Okay, lecture 18, real distinct eigenvalues. So we'll look at the general solution and then three cases, one positive and one negative eigenvalue, two positive eigenvalues, and one zero and one positive eigenvalue. There are other cases, but they can be derived from these. So this is the basic idea. We can write systems in matrix notation. And what's the general solution if we get two real eigenvalues? Well, we know these things, right? So we know, which we showed last time, that if we have these eigenvalue eigenvector pairs, these two are solutions. We know that the solution space is a subspace. So if you add solutions together, you get a new solution. Lambda 1 is not equal to lambda 2. That means V1 and V2 are definitely linearly independent because they belong to different eigenvalues. And V1 and V2 are two-dimensional vectors because we're only in two dimensions. So from 1 and 2, every linear combination of y1 and y2 is a solution. And from 3 and 4, every possible initial condition, right, if you think of the plane as being our initial conditions, then every possible initial condition can be reached by V1 and V2. And so that means that the functions actually span the entire plane. So let y prime of t equal my of t be a system of equations, lambda 1 v1, lambda 2 v2 as real eigenvalue eigenvector pairs with lambda 1 not equal to lambda 2. So any initial condition is a linear combination of v1 and v2 because are linearly independent. So Li, that's supposed to be a comma there, and are in two-dimensional space. So they're basis, right? There's two of them and they're linearly independent in a two-dimensional space. So V1 and V2 span the plane. And so that means no matter what vector we pick, no matter what initial condition we pick, we can write it as a linear combination of K1 V1 plus K2 V2. And then the solution to this initial value problem with this initial condition is that. And how can we tell? Well, we know this is a solution. We know that that is a solution. And from part one, what we just did above, we know that y of 0 equals K1. Sorry. So that makes y of t equal to K1 e to the lambda 1 t times V1, because that's y1. And y2 is K2 e to the lambda 2t times V2. So y at 0 is K1 e to the 0 times V1 plus K2 e to the 0 times V2. But e to the 0 is just 1, so y of 0 equals K1 V1 plus K2 V2, and we chose K1 and K2 so that this sum actually equals the initial conditions that are given. So it's the solution to that equation. Okay, so one way to think about this theorem states that y1 and y2 span the solution space. And so this gives us a method for solving these sorts of problems. Y prime equals my with initial conditions y0. We can find the two eigenvalue eigenvector pairs, lambda 1 v1, lambda 2 v2, and the solutions. And the solution is a linear combination of those two. So what we're going to do is find the eigenvalues and the corresponding eigenvectors, and then we can put together the solutions. So we want to find the solution for this initial value problem, graph the vector field, and sketch the solution. How many different types of solutions are there, and what happens as t goes to minus infinity? So here we can write this as, if we set y equal to x of t, y of t, and then y prime is the derivatives of the two. Right? And so y prime is these two things. And we'll take M to be the matrix of coefficients. And that means then that y prime equals M times y. So we need the eigenvalues and eigenvectors of this matrix. Of that matrix. So to find eigenvalues, that's going to be determinant of the matrix M minus lambda times the 2 by 2 identity matrix equals 0. M minus lambda I2 is 2 minus lambda 4, 1 minus 1 minus lambda. It's what you get when you subtract lambda off from the main diagonal. So the determinant of M minus lambda I2 is 2 minus lambda times minus 1 minus lambda minus 4. So it's this times this minus 1 times 4. You multiply that out and you get lambda squared, and then I have plus a lambda minus 2 lambda, so that's a minus 1 lambda. Minus 2 minus 4, that equals lambda squared minus lambda minus 6. So our characteristic equation is lambda squared minus lambda minus 6 equals 0, and that can be factored. Lambda minus 3, lambda plus 2 equals 0. So our two eigenvalues of lambda 1 equals 3, lambda 2 equals minus 2. Okay, so now we have eigenvalues. We need to find an eigenvector for lambda 1 equals 3. How do we do that? An eigenvector is a solution to MV, where M is the matrix above, equals 3V, right? So V is the eigenvector, 3 is my eigenvalue. Or we can find the eigenvector by moving this over. Remember that subtracting 3 is the same thing as 3 minus I2. So it's this matrix. So what we do is we take this matrix up here, which is M minus lambda I2, and just plug in 3 for the lambda. And we'll take x1 and x2 to be our knowns. Those will be the x and y coordinates of our eigenvector. So what we've done, if I can just scroll up a little bit, we take this matrix, which is M minus lambda I2, we plug in lambda equals 3 and set it equal times x1, x2 equals 0 and see what we get. And so this equation becomes minus 1, 1, 4. Oops, that should be a 3, not a lambda. Minus 4, x1, x2 equals 0, 0. And what you should always get at this point is that your rows are multiples of each other, right? And so we take the top row, multiply it by 4, minus 4, we'll get the bottom row. So that means we can take either row. I'll take minus 1 times x1 plus 1 times x2 equals 0, or x2 equals x1. Right, because the rows are multiple, because, if I tried to row reduce it, the bottom row would just give me a row of zeros. So that means I've got a parameter, and so I can take whatever values of x2 and x1 I want. I'll take the simplest one, I'll set x1 equal to 1 and x2 then is also 1. So my vector that goes with lambda 1 is 1, 1. So there's an eigenvector. So same procedure for finding the eigenvector for lambda 2 equals minus 2. We set up the equation 2 minus minus 2, 1, 4, minus 1. Oops, there should be a minus sign in there, minus 2. x1, x2 equals 0, 0. Right, so we subtract off the eigenvalue minus 2 from the main diagonal, multiply x by x1, x2, set that equal to 0, solve for x1 and x2. And there should be a parameter. So my equation here becomes 4, 1, 4, minus 1, minus minus 2 is 2, minus 1, 1, x1, x2 equals 0, 0. Rows are multiples. So I get 4x1 plus x2 equals 0. I can take x1 equal to 4 and x2 equals, no, x1 equal to 1 and x2 equal to minus 4. And that's a solution. And so that gives me the eigenvector 1, minus 4. Great. So solution, general solution. Y equals k1 e to the 3t, because it's one of our eigenvalues, times the eigenvector for 3, which is 1, 1, plus k2 times e to the minus 2t times the eigenvector for v lambda for minus 2, which is minus 1, 4. So that's our general solution. What are k1 and k2? We find those from the initial condition. In the initial condition that we had, was x at 0 equals 1, y at 0 equals minus 1. Let's just double check that that's correct. Yep, 1 minus 1. So find k1, k2 from the initial conditions. So using this formula, what's y at 0? Y at 0 is equal to k1, 1, 1, plus k2, 1 minus 4, and that should be equal to 1 minus 1. Right, and we need to solve this for k1 and k2. So this is just now an augmented matrix again, right? We want 1, 1, 1 minus 4, 1 minus 1. This is our column for k1. This is our column for k2. This is the vector we're trying to solve. If we reduce this, we can subtract the top row from the bottom row. We get 1, 1, 1. We leave the top row alone. 1 minus 1 is 0. Minus 4 minus 1 is minus 5. Minus 1 minus 1 is minus 2. So we can actually stop the reduction here. Just say we get minus 5x2 equals minus 2, which means that x2 is 2/5. That was this lower equation. The upper equation is x1 plus x2 equals 1. So if x2 is 2/5, x1 has to equal 3/5. So the solution, the full solution is what? It's y, don't know what happened there. Y equals k1 Oh, this should be x's. These are k's. K1, K2, K2, K2 equals 2/5, K1 equals 3/5. 3/5 e to the 3t times 1 plus 2/5 e to the minus 2t times 1 minus 4. So there's our solution. Great. What does the solution look like? What does the vector field look like? So we've got these questions. What is the vector field? Sketch the solution. What happens as t goes to minus infinity, as t goes to plus infinity? How many different types of solutions are there? So what is our vector field going to look like? Let's zoom out a little bit, give myself a little more space. Okay, what is our vector field going to look like? Well, we'll put in an x-axis and a y-axis, x and y. This is the eigenvector corresponding to 1, 1. And we know that e to the 3t times its eigenvector is itself a solution. And if we multiply that by any constant, in particular minus 1, 1, we get another solution. And also, we know y of t equals 0 is a solution, because 0 is in our subspace, it's always in the solution space. So 0 is a solution, that's just this constant point there. 1, 1, if the vector is 1, 1, that goes out that direction, so we get a curve out here. And this is the solution e to the 3t y1. As t gets bigger, you go away from the origin. As t goes to minus infinity, you crawl in towards 0. Minus 1, 1 is down this way, and e to the 3t minus 1, 1 is also a solution, but it's a separate solution. So this line actually has two separate solutions on it. So likewise, e to the minus 2t, 1 minus 4, so 1, 2, what's going on here? 2, 2, 3, 4, 1 minus 4 is this line. And so this is e to the minus 2t, 1 minus 4. That's the solution. Since it's a negative exponent, it's going in. And if we draw the other half, e to the minus 2t minus 1, 4 is also a solution. So right now in this picture, I have 5 separate solutions. 2 for e to the 3t, 2 for e to the minus 2t, and the origin itself, which is an equilibrium solution. So what do all other solutions do? Well, if we look at this general solution, right, y equals k1 e to the 3t, y11, k2 e to the minus 2t. Let me just rewrite it down here. Y of 2 t equals k1 e to the 3t minus 1 plus k2 e to the minus 2t 1 minus 4. As t goes to infinity, this one dominates, this one goes to 0. As t goes to minus infinity, this one goes to 0, and this one becomes very large, it dominates. So in fact, as we go to positive infinity, this term, the second term, just disappears. And so that means we'll end up being asymptotic to the first one. And if we go to minus infinity, the first term disappears, which means we'll end up being asymptotic to the second one. So all our solutions, and in particular the solution that starts at 1 minus 1, x equals 1, y equals minus 1, which is there, what's that solution going to do? In backwards time, it's going to be asymptotic to this, and in forward time, it's going to be asymptotic to this one. And all the solutions here will follow that same pattern. All the solutions in this quadrant be asymptotic to the negative exponent, and then they shift over and become asymptotic to the positive one, asymptotic to the negative one, shift to be asymptotic to the positive exponent, negative exponent to positive exponent. So that's what all the solutions are. So we actually have 4 classes of solutions that look like basically hyperbolas, right? This region, this region, this region, and this region, everything just flows from negative to positive. And then we have these 4 eigenvector solutions and the origin. So that's what the base plane would look like. If you want to know what the vector field looks like, you can just add a bunch of stuff. Vectors going this way. So what happens as t goes to infinity for all solutions except this one, and the origin? You go to infinity, and you go out asymptotic to this eigenvector. As t goes to minus infinity, everything comes from the eigenvector with a negative exponent, except this one, which comes from 0, and that one, which in backward time goes to 0, and of course 0 just sits where it is. Okay, what about 2 positive eigenvalues? General solution for the system below, graph the vector field. How many different types of solutions are there? So we know what we're about now. This is our matrix. Need eigenvalues. How do we find eigenvalues? You take 5 minus lambda, 6 to 4 minus lambda. Take the determinant of that. Should have written determinant first and set it equal to 0 and solve for lambda. So we get 5 minus lambda times 4 minus lambda. So this diagonal minus that diagonal, minus 12 equals 0. That's our characteristic equation. What do we get from that? We get lambda squared. I get a minus 5 lambda and a minus 4 lambda. That's minus 9 lambda. And then plus 20. Minus 12 equals 0. Can't forget the minus 12. So our equation is lambda squared minus 9 lambda plus 8 equals 0, which factors lambda minus 8, lambda minus 1. So lambda 1 equals 8, lambda 2 equals 1 are our 2 eigenvalues. Now we need to find eigenvectors. So eigenvector for lambda 1 equals 8. We take this matrix and replace all the lambdas with 8s. So that gives us 5 minus 8, 6, 2, 4 minus 8. And then we need to find our 2 components, x1 and x2, by setting that up. Simplify it, you get minus 3, 6, 2, minus 4. And here, just as a check that you solve for eigenvalues correctly, rows are multiples of each other, right? So if you multiply the bottom row by 3 halves, minus 3 halves, you get the top row. So I can pick either minus 3x1 times 6x2 equals 0 or 2x1 minus 4x2 equals 0. I'll go with 2x1 minus 4x2 equals 0, or x1 equals 2x2. So we'll set x2 equal to 1 and x1 then is 2. And our eigenvector is 2, 1. What about eigenvector for lambda 1 equals 1? Same deal, 5 minus 1, 2, 6, 4 minus 1. Subtract the eigenvalue from the main diagonal, 0, 0. And that becomes 4, 6, 2, 3. And again, we see that the bottom row and the top row are multiples of each other. So that means we did correctly find our eigenvalues. So I'll take the bottom row, 2x1 plus 3x2 equals 0. What are convenient numbers for this? Well, I'll take x1 equal to 3 and x2 equal to minus 2. And that would give me 6 minus 6 equals 0. So v2 is 3 minus 2. So what's the general solution to our equation? Y equals k1 e to the 8t 2, 1 plus k2 e to the t 3 minus 2. Good. And since we weren't given an initial condition, that's all we can do. So what does the phase plane look like? So let me bring down y equals k1 e to the 8t 2, 1 plus k2 e to the t 3 minus 2. And scroll down a little bit. We need to remember that this in itself is a solution, and this part by itself is also a solution, because that gives us the basic thing that we need. So what do we have? We have 2, 1, 1, 2, 1. So that would be along that line. That's one eigenvector. And it's got a positive eigenvalue, so we're going out. This is e to the 8t times 2, 1. And then we have the flip side of that going out this way. This is e to the 8t times minus 2 minus 1. And 0, of course, is its own solution. Now this one, 3 minus 2, this solution, we have 3 minus 2, so 3 minus 2 would be out to about here. This is e to the t times 3 minus 2, and we're going out this way because it's a positive exponent, and then opposite it, we have e to the t minus 3, 2, and that's going out the other way. So 5 solutions here for 2 solutions involving the eigenvalue 8, 2 solutions involving the eigenvalue t, and the origin. So what does everything else do? Well, for very large t and negative, so if t is negative, the higher exponent goes to 0 faster. So that means my solutions are going to come out tangent to these 2 eigenvalue solutions. So in backwards time, we're going toward the origin, but we're not just randomly going towards the origin. We're going towards the origin tangent to this vector. As t goes to plus infinity, tangent to that line. The roles switch. E to the 8t 2 minus 1 dominates. E to the t 3 minus 2 also goes to infinity, but it's going to infinity much slower. So we're going to end up being tangent to, not tangent to, but parallel to the higher exponent. So what are my solutions going to look like? Well, they have to be coming from here and then end up tangent here and here. So my solutions will look something like that. We're going out. So everything goes out away from the origin. and everything ends up parallel, more or less, to these things and tangent to the smaller eigenvalue as we're going back to infinity. Last case, 1, 0, 1 positive eigenvalue. This should be example 3. So how do we go about solving this? We find our matrix is 6, 4, minus 3, minus 2. We need determinant of m minus lambda I2 equal to 0. And that means we need the determinant of 6 minus lambda, 4 minus 3 minus 2 minus lambda with 0. I keep forgetting to write in determinant. We need the determinant of that matrix equal to 0. So again, we multiply down one diagonal and subtract off multiplying down the other diagonal. So we get 6 minus lambda minus 2 minus lambda plus 12. If we multiply that out, we get a lambda squared. I get a plus 2 lambda minus 6 lambda, which is a plus 2 lambda minus 6 lambda is minus 4 lambda. And then a minus 12 plus 12. So lambda squared minus 4 lambda is our determinant. So we have lambda 1 equals 0 and lambda 2 equals 4. Those are our two eigenvalues. Eigenvalues. So we need eigenvectors. Eigenvectors for lambda 1 equals 0. Well, we just take our matrix and subtract 0 off it. X1, X2 equals 0, 0. Simplify what's inside the matrix, and lo and behold, it's just our original matrix. So you can look at a matrix, and if the rows, 2 by 2 matrix, if the rows are already multiples of each other, just when you started, like here, you take the top and multiply it by minus the bottom, and multiply by minus 2, and you get the top, then you know 0 is going to be one of the eigenvalues, which doesn't help you as much as one would think. So since I don't like minus signs, I'll go with 6x1 plus 4x2 equals 0, divide through by 2, that gives me 3x1 plus 2x2 equals 0. So I'll take x1 equal to 2 and x2 equal to minus 3. And so that gives me v1 equals 2 minus 3. For lambda equals 4, six minus 4, 4 minus 3 minus 2 minus 4, x1, x2 equals 0, 0. So that's 2, 4 minus 3 minus 6, x1, x2 equals 0, 0. So, right, bottom row is minus 3/2 times the top row. So we'll go with 2x1 plus 4x2 equals 0. Divide through by 2. x1 plus 2x2 equals 0. So what's a solution to this? A convenient solution is x1 equals 2, x2 equals minus 1. So v2 is 2 minus 1. So what's my solution? Y of t equals k1 e to the 0t times 2 minus 3 plus k2 e to the 4t 2 minus 1. And this is a little bit weird because it's y of t equals k1 2 minus 3 plus k2 e to the 4t 2 minus 1. So what does our solution does our space look like? Here's my x-axis, here's my y-axis. I have this vector, which is 1, 2, 1, 2, 3 down here. So k1, 2 minus 3. If k2 is equal to 0, right, then we're on this line somewhere. But there's no t here. Right? These solutions are all constant. So what I actually have here for my 0 eigenvector is I have a whole line of equilibria. Each point on this line is an equilibrium solution. These are all equilibriums. The other line I have is 2 minus 1, which is like there. So it's a line like this. And positive exponents, so we're going out. So what actually is going on here? If we actually write this out for x and y, you get x is 2k1 plus 2k2 e to the 4t. Y is minus 3k1 plus minus k2 e to the 4t. So I can solve this equation for e to the 4t, x minus 2k1 over 2k2 equals e to the 4t, and then plug it in into the y equation. Right, we can actually solve that for y in terms of x. And what we actually have here, this is a line, right? X is right there. The slope is going to be k2 divided by 2k2. It's actually going to be 1/2, and the minus 1/2, and the y coordinate will depend on k1 and k2. So what are all the solutions look like? Every solution in backwards time, as t goes to minus infinity, if this goes to minus infinity, you end up at one of these points. And forward times, it just runs out parallel to that. So all these solutions are parallel. And then we have other solutions going out this way. So solutions here, there's a line of equilibria, and the solutions are lines, and all the solutions are parallel to the eigenvector eigenvalue pair that's not equal to 0, and they just run out parallel to each other. And that gives us the phase plane for a 0 eigenvalue.